In this video, we are going to look at particular cases where the gradient of certain functions has some physical significance. Now we'll start with this example here, which we met last time. If I were to perform some sort of experiment and measure the displacement of a body every so many seconds and plot it on a graph, I might get a graph that looks like this. This graph is in the form y equals mx plus c, where m is the gradient and c is the y-intercept. And our displacement as a function of time is equal to the gradient of this line equals time plus that initial displacement. So we've just substituted in what the y-axis represents, what the x-axis represents, and the physical significance in this case of the y-intercept. So what about the gradient? To calculate the gradient, we take 2 points on the line as far apart as we can from each other. We measure from the graph the difference in time represented by this space on the x-axis between these 2 points and the difference in displacement. That's this difference on the y-axis. So our gradient, m on this equation, is delta s divided by delta t. Now we define a rate of change of displacement as a velocity. That's something that physicists have chosen. That's a definition that we have come up with. We have a quantity that we have invented called velocity, which is the rate of change of displacement. And on a displacement time graph, that can be determined by measuring the gradient. Here I've just put a few more examples where definitions involve these gradients. So acceleration is defined as the rate of change of velocity. A force is defined as a rate of change of momentum. A potential gradient is a field strength. This is Faraday's law, that the rate of change of flux linkage is proportional to the EMF. Over here we've got that the rate of flow of charge is defined as the current. And this one here, well, this is the definition of some sort of exponential decay. In this case, maybe it's radioactive decay. So these gradients appear all over physics, and we define what the physical significance of that gradient is. But don't get me wrong, these gradients have physical significance. Take the example of current. Current was discovered before charge was. Now you'll see expressions written like this in your A-level. However, the universe isn't always so kind as to give us uniform field strengths, or uniform EMFs, or uniform accelerations, or uniform velocities. So let's stick with this example, with velocity being the gradient. And you can see we've got a problem. This is no longer a straight line. So let's say we want to calculate what the velocity is at a time t prime. It's just some time, it could be 2 seconds, it doesn't matter. We need to find out what the gradient of the line is at this point. The problem is the line's a curve. Now, graphically, we could draw a tangent at that point and measure the gradient of that tangent, and that would be fine. But there is a way of writing a function which tells you what the gradient is for every point on this graph. So perhaps this graph is a model representing some sort of accelerating body. The displacement is a function of time, and perhaps this is the function. Well, in the next video, I'm going to show you how you can analyze this using calculus.